Right, now it is started. Thank you. Right. Okay, thank you. So today we will see the lecture 19. So, now you can see the screen, right? Yes. Hello.
Yes, sir.
Okay, good. So we start with acyclic graph. So what is an acyclic graph? So a graph G is called acyclic if there are no cycles in G. Okay. So if you have a graph where there is no cycle, then it is called an acyclic graph. For an example, suppose you have this graph. So this is just one. Now this is not acyclic, right? Because it has a cycle. Now if you have say this one and this one, so these two disconnected graph. So what is disconnected? I will tell you. So this one. Now this is also acyclic, right? Because this graph does not have any cycle. But note that acyclic graph can be connected or can be disconnected. Okay, so the acyclic graph means there is no cycle. Fine. Now what is a connected graph? You already know the notation and the definition also. So what is a connected graph? So a graph is called connected if for every vertices UV, okay, there is a path in G from U to V. For an example, if you look at this graph, the first one, so this is your connected graph because if you choose any two vertices, say this one and this one, so you have a path, this, right? So this is connected. But if you look at this graph, then it is not connected. Why? So if you choose this is your U and this is your V, then there is no path from U to V, right? So this is a disconnected. Now what is a connected component? Now also it is also clear. Now a connected component of G is a maximal connected subgraph of G. So that is, if you look at this one, so this is one maximal connected subgraph, right? So this is one component. And if you look at this, so this is another component. So this is a disconnected graph with two components. Now what is a complement of a graph? Now that is a very important concept, complement of a graph. Now what will we do to find a complement of a graph? So let G be a graph with the vertex set V and vertex edge set E. Now the complement of G will be denoted by G complement. So we generally write G power C. And the vertex set will be the same as V, but S set will be the complement of E. So what is the complement of E? So that's mean we will take all those edges which are not in G. Okay, and therefore we say that so there is an edge between two vertices UV in G complement if and only if there is no edge between X and Y in G. And if you take G union G complement, then you will have the complete graph with the on the n number of vertices. So for an example, we can see the examples. So for an example, you have this one. So this is your G. Now what will be G complement? Now you have four vertices. Now vertex set will be same, right? Suppose this is your say A, B, C, D. Then you have the same vertex set A, B, C, D. Now A is connected with B, A is connected with D. So these will not be edge in G complement. But here A and C does not have any edge, right? So therefore we have to add one edge this. And similarly, BD does not have any edge, so we have to add this. So we can add in this way. So this. So if this is your G, then this will be your G complement. Okay, so to find a complement of a graph, we keep the same vertex set, but we just choose those edges which are not in G.
Sir, you are not audible.
Yes, sir, you're muted, sir.
So when I was muted, so you did not
Just
hear.
last statement you said that which are not in G, the edges which are not in G. After that,
Okay, but I don't know how I got muted. Maybe someone muted me. Yeah, you should not mute me because here I have added all of you as a presenter only. Okay, so this is a complement of graph. So now there is a theorem. It says that either G or G complement is connected. So if you have a graph G, then either G is connected or its complement is connected. Now here we will have a proof. The proof is very simple. Now first we consider if G is connected, then we are done, right? Now we assume that let G be disconnected. Now in that case we will prove that if G is disconnected, then G complement should be connected. Why? So we take any two vertices UV from G complement. That is the same vertex here actually. So any two vertices V, any two vertices U and V. Okay. Now there are two cases. Now if there is no edge between UV in G, that's mean that is UV is not in not a edge in G. Okay. Then UV should be an edge in G complement, and then we are done, right? Now there are another case, say UV and edge in G, and in that case, since they are in U and V forms an edge in G, so therefore U and V those vertices lies right. Both vertices lie in a same connected component, but it is given that G is disconnected. So therefore we must have another connected component which contains another say one vertex say W. Right. So therefore, since U and W are in different component in G, so therefore there is no edge between U and W in G. So therefore there is an edge between U and W in G complement, and similarly there is an edge between W and V in G complement. So therefore U W V forms a path in G complement from U to V. So we prove that if we choose any two arbitrary vertices U and V, then either U be an edge in G complement or there is a path from U to V in G complement. So therefore G complement must be connected. So we are done. So any doubt in this proof? Or do you want to see this in terms of picture? Is that fine? Yes? Or shall I explain again in terms of picture?
Yes, sir.
What is? Fine or go with the picture?
Fine.
Okay, thank you.
Please explain again.
Okay. So so we have proved that. So we assume that here. So if G is connected, then we are done. Now we assume that G is disconnected. Okay. So since G is disconnected, so say this is G. Okay. Now say first of all, so this is your U and say this is your V. Okay. So this is your U and this is your V, or this is your V. It also is possible. So this is your U and this is your V, or this is your V. Then obviously UV is not in G, right? So UV, this is not in G. So that implies UV that is in G complement, right? So therefore in G complement, there is an edge between U and V. Okay, so how will you prove that G complement is connected? So we will choose any two vertices UV and we will find one path from U to V. So in that case, we have already a path. In fact, we have an edge from U to V. So we are done. Now suppose this is your V. So that's mean UV and edge in G. Okay. So UV and edge in G. Then that's mean UV should be in one component, one connected component, right? Now, since G is disconnected, so we have another connected component other than this, and say we choose one vertex W from here. Now, since UV is in the one component and W is a different component, so UW and VW, they are not in edge of G, and that imply UW and VW both are in G complement, and then we have a path U to VW. So we have a path P3 UWV from U to V. So in any case, if you choose any two vertices U and V, so you have a path from U to V in G complement. So therefore G complement is connected.
Sir, excuse me, sir.
Huh.
Sir, it may also happen that G is also connected and G complement is also connected.
Yeah, that is fine.
Okay, sir.
That is fine. What we are saying that we are not saying this is the statement. We are saying that either the graph G or its complement is connected. We are not saying that one of them is true. Both can be true. But we are saying that one of them should be connected. Okay, both can be connected as well. Okay, if both are connected, then we are done. So that is the reason if G is connected, then we are done. So we will not check for G complement. It can be connected, it can be disconnected. That does not matter. One of them is connected, so we are fine.
Okay, sir.
Okay, so it is saying that at least one of them is connected. Okay.
Sir, in the
Ah.
complement graph, do we have these additional edges, or we remove the older edges and make these additional edges?
Yeah, we delete the original edges. Obviously. We have proved, we have given that one, right? You see this one. So if this is your G, so this is your G complement. So here AB was an edge. So AB should not be edge in G complement.
Okay, sir.
Okay. So complement means one. So if you can say that UV is an edge in G complement if and only if it is not edge in G. You can see this one. So there is an edge between X and Y in G complement if and only if there is no edge between X, Y in G. It is if and only if condition. Okay. So if you take G intersection G complement, that will be just the discrete n vertices. That's all. Okay. Now, what is the difference between tree and a acyclic graph? So, as I told you that acyclic graph can be disconnected, but tree is connected. So, generally, a connected acyclic graph is called a tree. For an example, this one. So, this is a acyclic graph, but this is not a tree. But this portion is a tree, and this portion is a tree. Okay, so tree should be a acyclic graph and connected. Okay, and if you take this union T1 union T2, then that will be acyclic graph. So acyclic graph means it can be disconnected, and it means that only it does not have any cycle, and T means it does not have any cycle and it is connected. Is that fine? Okay. Now the theorem says that every non-trivial tree has at least two vertices of degree 1. Okay, so if you choose any non-trivial tree, then it must have at least two vertices of degree 1. Okay, so we will see that. So what we'll do, so we will take, let P be a longest path in T. Okay, so T, what is T? T is the tree. Okay, T is the tree, and we choose one longest path. So we can write actually. So first we draw. So this is a tree. Okay. Now actually here I have already 4 vertices of degree 1. But anyway, so you can choose any tree, and what here I'm saying what we choose that. So let P be a longest path in T. Okay. So that's mean take this one. 1, 2, 3, 4. Oh, sorry, 4. So you can choose 1, 2, 3, 4, 5. Oh, you can have another one. So choose this one. This is the longest one. 1, 2, 3, 4, 5. So this is your P. Okay, choose a longest path. So longest path may not be unique. You may have more than one longest path. So let's say this is your P. Okay, and let X and Y are the initial and final vertices of P. Say this is your X and this is your Y. Okay, now we claim that degree of X and degree of Y both are 1. We will actually claim that. So if you have a longest path, then, and if you take the initial point and final point, their degree should be 1. Okay. Now without, so for an so by a contrary, so suppose this is not true. Suppose degree of Y is bigger than 1. Suppose, then we will get a contradiction. Okay. Now how we will get a contradiction? Say this is a longest path and say this is your a vertex A. Now since d of y greater than 1, so therefore we must have another vertex z, and yz will be an edge, right? Now that z should not be in P, because suppose this z is this one. Okay, suppose this is your z, then you have a cycle. Right? Or you are confused with this one. Okay, I'm going this again. So we don't know what is a tree. Okay, we don't know what is a tree. We just take first the longest path. So this 1, 2, say 3, 4, 5. So this is your P. Okay, and this is subgraph of that subgraph of tree. Okay, and this is your X, this is your Y, and this is your A. Now we claim that degree of X and degree of Y both are 1. Now suppose degree of y is bigger than 1. Okay, then this is A, and so there must be another vertex Z. Now there is one possibility that that Z should maybe in P, but that Z cannot be in P. Why? So if this is your Z and if this is your edge, then we have a cycle. So this is not possible. Right? Because you have a tree. Tree does not have any cycle. So Z cannot be this vertex. Okay? Then what should be Z? Then Z should be in this way. This way. The other vertex other than P. And then, so this was your P. So P union YZ. This is another path. And that is the longer than P. So that is a contradiction because we have chosen the longest path P. Okay, so therefore, if you have a non-trivial tree, then it has at least two vertices of degree 1. Okay, is that fine with everyone? Why there is no response? Good one. So what is a non-trivial mean? Okay, so non-trivial means it is not a single vertex. Since it is a connected, right? It can be on a single vertex. So this is also a tree. So this is a trivial tree. So non-trivial means it must have at least one edge. Okay. So non-trivial means should have at least one edge. Okay. The proof is very simple actually. So all the proof related to tree is very simple, and you have to just write the proof in terms of it does not have any cycle. So that's all. Now recall that what is a cut vertex? So a cut vertex in a connected graph is a vertex whose deletion disconnects the graph, right? So that's mean if we delete the vertex, then you have a disconnected graph. So that is called a cut vertex. And similarly, cut edge is if you remove that edge, then that will disconnect the graph. For an example, suppose this is your graph. Now, can you give me one cut edge from this graph? Can you give?
No, no, sir.
No, there is no cut edge, right? Is there any cut vertex?
No, sir.
No. But if you look at this one, say A, B, C, D. Now, can you tell me one cut edge?
Remove BC.
Any edge is a cut.
Any edges. So if you remove AB, then the graph will be this A and this graph. This is A, B, C, D. If you remove the edge AB, right? Okay. Now, can you give one cut vertex?
B and C.
Right, B and C. Now, if you remove again B, then you have this and CD. Note that when you remove an edge, then we will remove only the edge, not the endpoints. But when we remove the vertex, then we remove the all the edges contains with the vertex. You have to remember that one. That was the definition of removing edge and removing vertices. Fine. So when we remove B, then we have to remove the edge BC and BA as well. But when we remove the edge AB, we will remove only the edge AB, not the vertices A and B. And that is the natural one, right? Otherwise, you cannot draw the other edges. Now that is a simple proof now. Now it says that in a tree, every edge is a cut edge. We have already seen that here. This is a tree, and we have proved, we have seen that every edge is a cut edge, right? And also every non-pendant vertex in a tree is a cut vertex. And here also we have seen that. So A and D, they are pendant vertex, right? So they are not cut edge, but non-pendant vertices B and C, so they are vertices. And A and D, they are pendant vertices, so they are not cut vertices. So here is the proof. So first we prove that any edge of a tree is a cut edge. So how to prove that? So let X, Y be an edge in T. Okay, and remove this. Now we actually claim that that should be disconnected, right? So as we have seen here, that is disconnected after removing any edge. Now suppose if possible, that is connected. If possible, still after removing XY, T dash is connected. And then since T dash is connected, then P is a path. So there will be a path P from X to Y in T dash. And if there is a path from X to Y in T dash, and this path P will not contain the edge XY, and then if you add XY, then it will be a cycle, and that is a contradiction. So therefore T dash must be disconnected. So we are done. Now similarly, let X be a non-pendant vertex of T, and say let Y and Z be adjacent to X. Now if possible, T dash, T minus X is connected. Since T dash is connected, so there is a path P in T dash from Y to Z. And obviously this path will not contain X because X is not in T dash. And therefore if you take P union these two edges, then that will be a cycle in G. Sorry, cycle in T. So we have T. So there is a type, so that will be T. So this is a contradiction. Okay. So therefore every edge is a cut edge and every non-pendant vertex in a tree is a cut vertex. Okay. Now there is another theorem that is also simple. So as I told you, so any proof in this chapter is very easy, right? So now this theorem says that a tree of order n means with n vertices has n minus 1 edges. Okay, so if you take a tree with n vertex, then it must have only n minus 1 edge. Okay, you can verify this here. So here you have tree with 4 vertices, and you can see that there are only 3 edges. Similarly, you can see here this. So this is also tree, and you have 1, 2, 3, 4, 5, 6, 7 vertices. Now you can count the number of edges, that is 6. So 1, 2, 3, 4, 5, 6. So if you have any tree with n vertices, then it has n minus 1 number of edges. Now we'll prove this by induction. Now the base case when n equal to 1. So if you have only single vertex, then there is no edge. So that is true, right? So that is trivial true for n equal to 1. Now we assume that the statement is true for all n less than equal to k. Okay, and let T be a tree with k plus 1 vertices. Okay. Now since it has k plus 1 vertices, so it has an edge say xy, right? Because here n is bigger equal to k plus 1. Okay, so therefore it must have an edge. So take that take any one arbitrary edge xy, and we delete that xy, and we have t dash. But we have already proved that here any edge is a cut edge. So that's mean if you delete any edge, then that disconnect the tree. So therefore after removing xy, t dash will be disconnected and it will have exactly two components. So t dash has exactly two components, t1 and t2. Say with n1 and n2 vertices, where n1 plus n2 is k plus 1. Right? So t1 is a tree with n1 vertices and t2 is a tree with n2 vertices. And n1 plus n2 equal to k plus 1. So therefore by the induction hypothesis, since n1 is less than equal to k, so we have t1 has n minus 1 number of n1 minus 1 number of edges and t2 has n2 minus 1 number of edges. So therefore t has this number of edges plus this number of edges plus 1. Why plus 1? We are adding the xy and that is k. So therefore if you have k plus 1 number of vertices, then you have k edges. So therefore the statement is true for n equal to k plus 1. So therefore by the strong induction principle, we can say that for any n, every tree with n vertices has n minus 1 edges. Okay, and this number is exactly. So any tree with n vertex with n vertices has exactly n minus 1 number of edges. Okay, so tell me, so if you have any doubt on in this proof, is that fine?
Yes, sir.
Okay. Okay, so is there any student here from group 6? So I can see there are a number of students very less 40, but still, is there any student from group 6 here? Yes, no student? I think Akash Sinha from group 6, right?
Yes, sir.
Okay, so you today you have tutorial. Oh no, not today.
No,
Next
sorry,
Saturday.
Saturday.
From so we will have a class from 9:30 to 11, and then we will have a tutorial from 11:30 to 12:30. Okay, and I have assigned a new TA for your next tutorials. Okay, so I just want to confirm that there will be a tutorial on the Saturday from 11:30 to 12:30, and there will be a new TA who will take the tutorials because I got some objection from the students that the TA of group 6 is not sincere. So I just removed him from TA. So anyway, we go back to our lecture. Fine. So this is fine. That is a very simple proof. Now again, this is again very simple. Now it says that let G be a graph with n vertices and n and m edges. Okay, n vertices and m edges. Now if m is bigger or equal to n, then G has a cycle. Okay. Now here is the proof. Note that what we have seen here. So if a graph is tree, then it has exactly n minus 1 edges, right? So that's mean the number of edges is strictly less than the number of vertices. And here we are saying that number of edges is bigger or equal to n. Then we are saying that it has a cycle. But we did not mention that G is connected or not. Okay, we did not mention that. Okay, so first we had assumed that, so if possible, let G do not have a cycle. Okay. Now let G1, G2, Gk be the connected components of G. and let ni be the number of vertices of gi and mi be the number of edges of gi. Then obviously summation of ni is n, summation of mi is m. Okay. Now since it is given that m bigger equal to n, so therefore this sum is bigger equal to this sum, summation ni. So therefore we must have one I such that mi bigger than equal to ni. Okay. Now note that we assume that G does not have any cycle, right? We assume that G does not have any cycle. Therefore each of Gi does not have any cycle, and here Gi is connected. So therefore Gi is a connected acyclic graph, that is a tree. Okay, and also Mi is strictly bigger than Ni minus 1. Since Mi is bigger or equal to Ni, so that's mean Mi is bigger than Ni minus 1. So that is a contradiction because that cannot be a tree. Because we proved that for a tree, the number of edges is exactly Ni minus 1. But here Gi is a tree, but the number of edges is bigger than this. So this is a contradiction. So therefore Gi must have a cycle. So that is G has a cycle. So note that all the graph theoretical problems are this type of problems only. So you have to think and you have to write in that way. Okay, another comment. Right, obviously. So if you can prove by using Pigeonhole principle, you can always use that. So we always encourage that if you use some other part here.
Sir, because m is greater than equal to n and the edges are,
Right,
can we
yeah.
take edges as
Uh,
pigeons and what is the and
right,
was
good one. Yeah.
okay, sir.
Okay, so again, now here we have seen that m greater equal to ni, m greater equal to n, that is number of edges is bigger or equal to n number of vertices. Now we see that number of edges is strictly less than number of vertices minus 1. So let G be a graph with n vertices and m edges, and this is true. That is m is strictly less than n minus 1, then G is disconnected. Okay. Now again, this is a consequences of this theorem that any tree of order n has exactly n minus 1 edges. This is the consequence of this theorem only. Okay. So if possible, let G be connected. Now if G does not have any cycle, then G is a tree, and we have already a contradiction because for a tree we know that m equal to n minus 1, right? So anyway, so if we assume that if G has a cycle C, okay, say G has a cycle C, then what we can do, we can pick any edge E and we can remove it. Then we will not have the cycle, but still the graph will be connected. Right? And we do this one. We keep doing this one until we have no cycle. So we keep doing that. So after finite number of steps, since we are dealing with finite graphs, so after finite number of steps, we end up with a induced graph G tilde, where G tilde does not have any cycle. Okay, so being an acyclic and connected, G tilde must be a tree. So G tilde has n vertices. Now since we are removing just edges, so therefore edges of G tilde is less than equal to number of edges of G. Okay, and that is equal to m, and that is strictly less than n minus 1, and that is a contradiction because G tilde is a tree, and we know that a tree must have n minus 1 number of edges, but here we are getting that number of edges of G tilde is strictly less than n minus 1, so we have a contradiction. So therefore G must be disconnected. That is very simple proof. Okay. Fine. Now what is a spanning tree? So let G be a graph. Then a spanning tree of G just a subgraph which contains all the vertices. So that's sorry, and which is a tree. So spanning tree is a tree which contains all the vertices. The spanning tree may not be unique. For an example, say again you start with this one. Now this is a graph G, right? Now there are many spanning tree here, so we can have this one. So this is a spanning tree. Now if we choose this one, so this is also a spanning tree. Now there are many ways to get a spanning tree. So what you can do, suppose you have a graph. Now that if that graph has no cycle, then you already have a tree. Okay, and if the graph has a cycle, then we can remove one edge from that cycle, and after finite step you will get a tree. That is called a spanning tree. Okay. Now the theorem is every connected graph G has a spanning tree. As I told you. So how to get this spanning tree? So since the graph is connected and if G has no cycle, then it is a acyclic connected graph. So it is already a tree. Now suppose G has a cycle. Then what you will do? You just delete one edge from that cycle. Then that cycle will not be a cycle now, right? And since we remove only one edge, the graph will be still connected, right? And continue this, and after a finite number of steps, you get a spanning tree. So that's all. Is that fine? That every connected graph has a spanning tree? Can you see this? So don't go through that proof. Just tell me that. Can you see that one? So can you visualize that? Yes. So if you have any doubt, you should ask. For an example, if you have just take this graph. Say you have this graph. Okay. Now note that. See, this is a cycle. So this is a cycle. Now we can remove any one of these edges. Say remove this one. Okay. Then again you have a cycle, the big cycle this. Right now again you can remove this one. Then you get a spanning tree. This. Right? So you can just remove these two edges and you get a spanning tree. You could have removed the other edges as well and you can get a different spanning tree. Okay, so a connected graph always have a spanning tree. Okay, is that fine at everyone? I don't know why there is no response from the students.
Yes, sir.
Okay, fine. Okay, now there is a important concept that is called a planar graph. So what is a planar graph? So planar graph means if a graph can be drawn in a plane without any intersection. Okay, then that graph is called a planar graph. Intersection means intersection on the edges. Okay. So tell me if you have this graph. Is this a planar graph?
No, sir.
No, sir.
Yes, that is a planar graph. Why you are not saying here? Why you are saying that this is not a planar graph?
So the diagonals are intersecting.
Yeah, but you can remove that one, right? So you can
Yes,
just,
sir.
instead of writing this one, you can draw in this way. That's all. That is the same graph, right?
Yes, sir.
So this is a planar graph. So what does it mean, the planar graph? If you can draw that graph in a plane such that there is no intersection on the edges. So you can draw this graph. So that is a planar graph. So there is no difference with this. You have to understand that in graph theory, there is no difference with this and this, because graph is not a picture. So both are same. Why both are same? Say, so this, so here the vertex set is 1, 2, 3, 4, and A set is 1, 2, 2, 3, 3, 4, 4, 1, 2, 4, 1, 3. So that is the graph. G equal to V comma E. Now that is the graph, and these two are just the visualization, and that is the main graph. That is the graph. Okay, and this graph can be written in a can be written on a plane with no intersection on edges. So therefore, it is a planar graph. Is that clear? So therefore, it is a
Yes.
planar graph. Okay. Now there is another concept called face. So what is a planar graph? Or what is a face of a planar graph? Now suppose you can draw a graph in a plane. Now if you remove this graph from a plane, then you have some connected components in a plane, and those connected components are called faces. For an example, can you tell me how many faces are there in this graph? Yes, how many faces are there? 1, 2, 3, 4, 5, 6. Faces means just the region bounded by the edges. Or if you remove the graph from a plane, then you have some connected components in the graph, in the plane, and those components are called faces. Now can you tell me how many faces are there in this graph?
5.
5. So can you tell me what are the regions? So this is one region, 1. This is 2. This is another one. And what are the other 2?
So we can like remove this the rectangular part, the left edge and the bottom edge and the diagonal one, and we will get the whole region. A combination of 1, 2, 3.
No. So if you have this 1, 2, 3, and this complement of this one, this is another one. So you have only 4 edges, 4 faces.
We cannot remove any edge.
See what we will do. You have a plane, okay, and you remove this graph from the plane. Then how many connected component will be there? So this will be one connected component. This will be one connected component. This will be one connected component, and the outside will be one connected component with a hole. Right? So we have 4 faces. Is that clear? There is 4
Yes,
faces.
sir. Yes, sir.
So can you explain again? Like, what do you mean by removing the graph from the plane?
Okay, suppose you have this graph, okay, and you remove this graph from the plane. Then you have 2 regions, right? One is
So
inside
removing
one.
means like we remove vertices and edges, then
No, you are removing that curve, that whole curve. You are removing that one
oh,
play from plane.
okay.
Okay, so just you just remove those region, that green one. You have just removed that part. Then you have 2 region, right? One is this region connected component, another one is disconnected component. So here number of faces is true, 2, right?
Yes, sir. Okay, sir. Got it.
This. See, here I have written that. So given a planar drawing of a planar graph, okay, the faces are the connected components of the plane after we delete the vertices and edges of the drawing. Or what you can do, you can take a piece of paper, your paper is like a plane only, and you can cut along these edges. And then you can see that how many pieces we will have after cutting along those edges. Okay. So planar graph means you can write this graph in a paper. You can write this graph in a piece of paper, in a single paper, right? And then now you can take a scissor and cut along these edges. And then you can see that how many pieces you will have now after cutting along this. So you have 1, 2, 3 and outside 4. You have 4 parts, right? So those 4 parts are faces. Is that fine? It is simple actually. Okay, fine. Now there are some examples. Every tree is planar. Now can you tell me, if you take a tree, so how many faces you will have? Yes, one face, right? Good. So because if you cut along the tree, still that will be connected. Now every cycle, if you take any cycle, Cn is planar. Now can you tell me how many faces we will have for a Cn, for the graph Cn? How many faces are there?
2.
Right, exactly 2. That inside one region and outside region. Now the complete graph K4 is planar. We have already proved it. See this one. This is complete graph with K4, that is planar, and we have seen that there are 4 faces. And the complete graph K5 is not planar. That's mean the complete graph K5 cannot be drawn in a plane, but for that you need a proof. You cannot directly say that okay, this is not planar because you cannot draw. But why you cannot draw, you have to show that. So you have to show some proof for that one. Okay. So we will see the proof in the upcoming slides. We will see the proof of this one, that K5 is not planar. And we will see that up from K5, K5, K6, K7 all are not planar. So only that K4 is planar. Okay. Now here is the Euler's formula. Now let G be a connected graph, connected planar graph, and phi be the f be the set of faces of the planar graph, or you can say the planar drawing of G. Then this number, that is number of vertices minus number of edges plus number of faces, is exactly 2. Okay. Okay. So we will prove actually by induction. Right? Or you can say that we will, since it is a finite graph, if G is fixed, we can say that by finite step only. We can see that. Okay. Now, first of all, if G is acyclic, but G is connected, so therefore G is tree, right? And then number of faces is exactly 1, as you already observed. And also we know that number of edges is exactly number of vertices minus 1. So therefore, this number, that is V minus cardinality of V plus 1, that is plus number of faces, equal to 2. So we are done. Okay. Now suppose G has a cycle and let E be an edge of a cycle. Then if we remove the edge E, then the number of vertices will be same. Number of vertices will be the same. Number of edges will be the 1 less, and number of faces will be 1 less. Why? You can see the region here. So here number of faces are 1, number of faces are 4, right? Now you can delete any one of the edges. See, if you remove, for an example, this edge, then see you are combining this region with this region. So now faces will be one less. Now similarly, if you delete this edge, then again the number of faces will be 3 because you are combining this region with this region. Right? So therefore, if you delete one edges from a cycle, okay, then your face will be one less. Okay, since deleting an edge involves in a cycle, merge two faces on either side of it. Okay, so therefore, say G be a graph, connected graph, and say after removing n edges, it becomes a tree. Now, since you remove n edges, so therefore you have a tree with v number of vertices and that mod of e minus n number of edges, and number of faces will be similarly mod of f minus n, and therefore this number equal to this number, and we have already seen that for a tree this number is 2, so that is 2. So we are done. Is that fine with everyone?
Yes, sir.
Okay, the proof is very simple. But though it is simple, but how to, now we know the proof, so therefore it is simple. But actually it was not simple before. So Euler proved that. So therefore it is written as Euler's formula. Fine. Now since, as I told you, we need that proof that K5 is not planar. Now for this we need a theorem. Now this is the theorem. Now it says that if G is a connected planar graph and number of vertices is bigger or equal to 3, then you have this relation. That is number of edges is less than or equal to 3 times number of V minus 6. Okay. So if number of edges is less than or equal to 3, then the theorem is obvious. Why? Because we have assumed that number of V bigger or equal to 3. So therefore this number is always bigger or equal to 3. Right? 3 into 3, 9 minus 6. So therefore it is always bigger or equal to 9. And if number of edges is less than or equal to 3, then it is trivially true. So therefore we assume that number of edges is bigger than 3. Okay. Now we count all the pair E comma F, where F is the face bounded by few edges including E. So we are counting all of this. For an example, I can show you what we actually count. Okay. So say this is your E1, E2, E3, E4, E5, E6, and say this is your F1, F2, F3, and F4. Okay, so what we will count? We count this. First count E1. Okay, now look at E1. E1 is this edge. Okay, so E1 involves in F1 and F3. So E1, F1, E1, F3. Okay, and similarly we count E2. Now E2, right? E2 is an edge and it has two sides, right? One side you have F1 and other side you have F3. Okay. Now look at E3. Now it has F2 E3 has F2 and F4. Similarly, E4, one side you have F4, sorry, F2, another side we have F4. Now look at E5. This is F1, E5, F2, and E6. One side you have F3, another side we have F4. Is that clear, the counting? So for each edge, you can see there are exactly two faces, because if you choose any edge, we have only two face involved with that edge in the either side. Right? So therefore number is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So total pair is 12, and 12 means 2 times number of edges. Is that fine?
Yes, sir.
Okay. So here we will actually count all possible pair EF, where F is bounded by few edges including E. Right? Now here we can see that this. Now if we count, since each edge bounds at most two faces, so therefore the number is 2E. So if we count first E and then F, then the number is 2E. Okay. Now we can count in the other way as well. So we can count first F and then E. Okay. Now this is one way we are counting. So first E and then F. Now we'll count first F and then E. Now we count in this way. Okay. So first we count F1. Now F1. So how many edges are there for F1? Can you tell me? What are the edges bounded? So F1, the region F1 is bounded by how many edges?
So E1, E2, E5.
Right, E1, E2, E5. So here E1, E2, E5. Okay, so this is for the F1. And similarly for F2, we have again 3. For F2 is 3, 4, 5. Right, 3, 4, 5. For 3, F3, we have 1 to 6. And for 4, this F4 is bounded by 3, 4, 6. 3, 4, 6. Okay. So if we count first F and then count E, then here in this case we are getting 3 times. So we are getting 3 times F. Right? For each F we are getting 3 edges. But it is for this one. But it might happen that any face, right? Any face might be bounded by more than 3 edges. So this number, this, if we count first F and then E, this number will be bigger than or equal to 3F. Is that clear? Why bigger than or equal to 3F? This counting. Here we are getting exactly 3F because if each of F1, each of region bounded by exactly 3 edges. But it might happen that each of region bounded by more than 3 edges, right? Then it will have 3 greater equal to 3. For an example, if you look at this figure, so this is F1 and this is F2. And you have E1, E2, E3, E4. Okay. Now, if you count this one, so E1, F1, E1, F2, E2, F1, E2, F2. In this way, E3, F1, E3, F2, E3, F1, E4, F1, E4, F2. So you get 2 times E, right? And if you look at first count this one, F1, and count this in this way, you have 4. Right? So in this way, you have 2 times E, but this number is bigger equal to 3 times F. Because this number is actually 4 mod F. And that is bigger equal to 3 mod F. Is that fine? That counting is bigger equal to 4, always bigger equal to 3 times mod of F. Or 3 times cardinality of F. Okay. So this pair is at least 3 times cardinality of F, and that is 2 times this. So therefore, we always have 2E bigger equal to 3 times this. Okay. So if we count first E and then F, then you will get exactly this. And if you count first F and then E, then you will get at least this. So therefore, 2E bigger equal to this. Now, if we put this relation here, you will get this. So we are done. You just check this one. Okay. And finally, we have this. So the average degree of vertices in a planar graph is strictly less than 6. Why? So we have this relation. So what is the average degree of a vertex? So that is 2 mod E by cardinality of E by cardinality of V, and that number is less than or equal to 6 minus this, and that is strictly less than 6. Okay. So therefore, the average degree of vertices in a planar graph is strictly less than 6. And as a corollary, you can say that a planar graph must have a vertex of order less than or equal to 5. Why? If each vertex has degree greater or equal to 6, then the average degree will be more than 6, more or equal to 6. But we know that average degree is strictly less than 6. Therefore, you must have at least one vertex whose degree less than.
Sir, you are muted again.
Any question? No, I'm not muted. Okay, okay. So from the next time, I have to put everyone as a attendee. Otherwise, some students mute me, I think. Okay, anyway. So the complete graph Kn is not planar. Why? Because Kn does not have any vertex of degree less than 6. So therefore, it is not planar. Now the complete graph K6 is not planar. Why? Because K6 has 6C2, that is 15 edges. But a planar graph with 6 vertices can have maximum these edges, right? So this is maximum these edges. So 3 into 6 minus 6. So it is 12. So a planar graph with 6 vertices can have at most 12 vertices, 12 edges. But K6 has 15 edges. So K6 cannot be planar. And similarly, K5 cannot be planar because K5 has 5C2 10 edges. But a planar graph with 5 vertices must have that many vertices, and that is 9. So K5 is not planar. So K5, K6, K7, K8, they are not planar graph. Okay, so we are done. So any question? Yes? Do you have any question on this? Okay, if there is no question, we can stop the recording and we can stop the meeting as well.